as we've been thinking about data structures and how we can store data and organize data and change data and things like that, it's important to think about this other question of how we identify data or how we identify things in the world in general. So we'll take a step back and think about this concept of identifiers. We see identifiers around us in the world all of the time. Your name serves sometimes as an identifier, though there's no rule that your name cannot be the exact same as someone else's name. It may be uncommon, but it is possible and it's allowed. Another way that there can be identifiers is to define systems for unique identifiers, where that identifying information should match to only one result, one person, one phone, one object, things like that. So some examples of these are social security numbers should be unique to every taxpayer in the U.S. Student ID numbers should be unique to every student within an institution. And even the items that you buy at the store have those barcodes which map to universal product codes, or UPCs, that again are supposed to match to only one product so that you know what the thing is that you're looking up the price for, or whatever other information, how much is in stock, or other things like that. So we have these all around us, and we come up with complex systems for them often for devising phone numbers or student ID numbers. Why? What benefits do those unique identifiers provide in the real world? And then we may be able to extend those kinds of benefits to the digital world and how we treat data. So I want you to pause for a moment and think about those unique identifiers you know about and ask the question of what benefits they actually have. Why do they exist? Pause, think about it. Some things that come to my mind when I think about unique identifiers is that they are very often used for looking things up. Right? If we go to the dining hall, they use my card sometimes with the ID number embedded into it to look me up and see what my dining plan is like. Or we can use phone numbers to look something up, or that kind of thing. Look up the business that called us to find out who it was. So they're often used for looking up information. And this is because they're unambiguous. So again, unlike, say, first names, which often can be non-unique, we know that if we look up something that's guaranteed to be a unique identifier, then we will find the thing that identifier maps to, and not several things or a random set of things or anything like that. They also often can be very useful for organizing or sorting things. So we could take student papers and I could sort them by student ID number if I needed an ordering so that you knew where to find your graded paper or that kind of thing. And so you may start to see how that could apply to us from a data standpoint too, that if we have unique identifiers for data, then they allow us to look things up and they allow us to organize or sort those things. Sometimes, I will note, they also contain information about the thing itself. So sometimes they contain information about the thing identified or represented. An example of this is, whether you know it or not, social security numbers are designed to have some embedded information about the person they represent, where they were born, the time period in which they were born, and possibly some other information I can't remember. And so sometimes that unique identifier is built from information about the thing being identified, and that may be useful to us as well. So if we think about looking things up, one of the data structures that we've spent a good amount of time thinking about that does allow us to look things up very easily is arrays. So in arrays, everything does have a unique identifier. The index serves as a unique identifier. It, however, has some weaknesses that we've explored a little bit on and off. One being that we usually assume every slot should be filled. There's not usually gaps left in an array. And we can design array structures or structures that use arrays that might allow for those gaps, but gaps in an array can cause problems. And the other issue that can come up with using arrays is if we tried to use an existing unique identifier, like a student ID number, and we tried to use that in an array as the index, then one, we would almost certainly have gaps. For example, if we tried to have an array of students in this course, there would be gaps in terms of array indexes, because not every 0000001 sort of ID number is going to be represented in this course. Some of them may not even exist at all. It may not be valid to have a phone number that is 000, etc. So some IDs may not be possible or may not be represented. The other issue, if we try to use existing unique identifiers and simply put them in as an index into an array, is that the size of an array to allow for real identifiers might be very, very large. If our student IDs are 8 or 9 digits long, we need that much of a size of an array to be able to use those directly as the index into that array. So the size would be the size of the actual identifier you're using, and a lot of that may be wasted space. Again, if you're dealing with students in this class, you need a very large identifier size, array size, therefore, with not much benefit from it for only a few students relative to that size. So to allow the ID as the index would create an array with a very large size, with a lot of wasted space probably. So one way that we move past this is to think instead of a new data structure idea, a map, in which we take some identifier that has to be unique, we'll call it a key, and we pair it with some value, the actual data, an image, whatever thing is that we're looking up, and we treat everything as a key and value pair. And you've seen this kind of thing represented in terms of data in lots of places. Databases do this. There is some key information that you can use to look up, and you get a large value comparatively. The key should be small. Doesn't have to be very, very small. Social Security numbers are somewhat long as integers go, but they are much smaller than, say, the full taxpayer record of the person whose Social Security number you're looking up. So the map is the abstract data type. All it specifies is that we have some key, some identifier, and that can be used to pair with some value, some real data that's often much longer and more complex. We can do things like sort based on that key, and we can do things like looking information up based on that key. Because map is only an abstract data type, it only talks about the operations we can do, not what data structure is used in the background, and not how fast those operations will be. That is the job of the programmer to decide what kind of data structure in the background makes sense. Maybe an array makes sense to store the data for that map. We've seen some weaknesses with it, but there are probably very good ways, and you will look at some of those. In your map project, you'll see over time writing a map that uses a linked list in the background to store its key and value pairs, and where that is good and where that is bad will vary. And you'll also later on work on a binary search tree, this much more complicated data structure in the background of a map, and see what features that gives us. Because remember, our goal as programmers, as computer scientists, is to think about the structure of our problem or of our data and choose the data structure and the algorithms and the implementation that match that best and give us the best performance. So you will see a little more of that as you look at the map activity sections A, B, and C. There is a section D that deals a bit with a linked list and might be helpful to you as you proceed into this map project where you'll be writing a linked list. So good luck.